Welcome to the exercise of the steel frame vibration. This exercise focuses about the determination of the dynamic properties of a structure. So if this is a civil engineering structure, for example, this is the bearing structure of a high-rise building, and if we say the wind is acting on the structure, this is random loading, and it would excite the building to vibrate. We would be interested, for example, to calculate the maximum horizontal acceleration at top floor. This would be a comfort criterion. But there are also other applications. For example, if this would be a industrial production site and we would have machinery in, so then the vibration created from machines could cause fatigue issues in the structure and so on and so forth. But in any case, we need to describe the structure dynamically. So as I said before, we have the eigenfrequency and the damping. We need the mode shape. We are looking here in this case only at one mode shape. You have already seen it. This is the mode shape, the first mode in the plane of the frame. We would like to know about the modal mass, which means that amount of mass which is activated by the vibration in the system. And we also would like to know the modal stiffness of the system that we can, in principle, condense. We can simplify the entire structure to a 1 degree of freedom system. This is quite common, and as long as our structure is linear, this is a very reasonable approach. So we have different steps in the exercise. The first is to calculate, to estimate the mass distribution of the frame. For that, you have to measure up the dimension of the individual elements, and assuming regular steel density, you have to calculate what is the mass of the individual parts, and then we concentrate the mass at the different floors. So we put actually the mass of all the elements here from the midsection between the two levels to the upper floor. So then we have the rest here, the halfway up and halfway down to the middle level, so that we have a lump mass here, and the same applies here for the rest for the lower mass. So then we have 3 mass points. And the next step is to estimate what is the vibration shape, which means the mode shape of the system. For that, we estimate the deflection form of the frame. So we pull statically here at the top part. This is not exactly the dynamic mode shape, but it comes quite close. And as I said before, if this would be a high-rise building, we treat these buildings very simplified. We assume that the mode shape is almost linear. So with that, we can apply certain methods, especially in wind engineering. And for that, the static deflection line of the frame is actually a quite good representation of the mode shape in this particular vibration. So we pull here statically, and then we measure the deflection at the different points. We load the system horizontally with different forces, and then we calculate the average, or let's say we normalize the local deflection here at the different floors with the maximum displacement of the upper floor. So, and this would be the principle of a mode shape, that we say that the modal displacement is 1 up here, and the rest refers to this normalized top deformation. So, and then we make the average of all these different deformation lines, and this would give us the estimate of the mode shape. Together with the lumped masses we have calculated before, we calculate the modal mass. So this is the modal deflection square times the mass, and the sum of all the, let's say, scaled masses. So then we have already 2 information. We have the mode shape, and then we have the modal mass of the system. And the resistance the structure gives to the load we put in horizontally, this is, as well as the mode shape, interpreted, or as well as the deflection interpreted as the mode shape. So the resistance, the stiffness we have here in this loading is also a good estimate of the modal stiffness. So if we have already the modal mass, we have the modal stiffness, so we can, in principle, already calculate, or we can give an estimate on what the eigenfrequency is. So, but we also would like to measure the eigenfrequency, because the first one, modal mass and stiffness, are estimates, so because we have the approximation of using static deformation. But we also would like to know what is the actual frequency. And with that, we also would like to know what is the actual damping of the structure. So, but one step at a time. So let us first talk about how to create the experimental setup for the static displacement and for calculating and for measuring the displacement under horizontal loading. Okay, we have now here the setup for the static deformation. We have here a loading gondola where we can put some weights in, and with increasing the weight we pull the frame here to the side. And on the other side we have at each level, at each floor, some dial indicators which are measuring the displacement. So, and this is giving us, if we have here these 3 points, of course at the bottom the deflection is 0. So, but then we have at 3 points the description of the static deflection under a single horizontal load, and this is the approximation of the mode shape. We do this in 4 steps. We at the beginning we make a reading of the dial indicators under 0 loading. Of course, here the gondola is already pulling, but this is our starting point. And then we load the gondola with 500 grams, and then after with 1 kilo, later 1.5, and at the end with 2 kilo weight. So, and this is now pulling the frame over, and for each individual loading we read the displacement and normalize each loading step. So this displacement of each loading step we normalize to the deflection of the top floor under the specific load configuration. Let's have a closer look at the dial indicators. So these instruments are mechanical dial indicators, and they show displacement on 2 scales. We have the outer scale with the large indicator, and the outer scale shows 1/100th of a millimeter displacement, and the inner scale with the short hand shows full millimeters. And of course, if the hand with the indicator on the outer scale has fulfilled 1 turn, so then the inner indicator has moved just 1 millimeter on the inner scale. We have in the outer scale 2 numbers. We have the larger ones and we have the smaller ones. So, and this is just to make it easier to read out the displacement. The larger ones are used, so they are increasing in number when the, let's say, the surface we are interested in is moving towards the dial indicator. So this is what I'm doing now. I'm pulling the frame towards the indicator. So therefore we have here 70, 80, 90 and so on. But in our case we go the other way. We pull with our weights the frame away from the indicator. So we could use the outer scale as well, since we are only interested in the difference. But if you like, or if this is easier to understand, we could also use the smaller numbers. So if we pull it away, so then would be the smaller numbers of the outer scale would then be increasing. So here we would be around 20, here 30 and 40 and then so on. So the same applies to the inner scale, so for the full millimeters. So, but the main or the most important thing is to keep track on the differences, and the most important thing in this case is to note down what is the start value. So the start value is already a bit tricky, so because the indicators do not stand necessarily on a particular value or on 0. So what we can do is we can, for example, in our case, we can turn the outer indicator so that the scale hits or is aligned with the outer hand. So and this is the value where we can start from. So this is again easier. to work with, but on the inner scale, so we just have to make a note that it's, let's say, here in our case, 6 point something millimeter as a start value. So, and from there on, we have to keep track how much we have in total displacement. So if I move now the frame away from the dial indicator and I release it, the indicator shows that the frame is not going back completely to its initial position. And this has something to do with that there is also friction, of course, in the different elements of the frame. So yes, it is an elastic structure, but when it comes to the, let's say, position or under the configuration under zero loading, it has, due to internal friction, can assume different positions. Very small differences, but the indicators do pick it up. So, and again, if I'm moving it towards the indicator and I release it, so it also comes to a different point. And if I'm now banging a little bit on the indicator, so of course, and I can try to bring it back to the initial position, but we should not worry too much about. So we start at a value and then we do the 4-step loading, then we unload it again and we do it again. So let's do it 2, 3, 4 times to have enough readings, to have actually a good database to make the average values and also to see how much does it actually differ each time we are using it. So far, so this was in principle that what there is to know for the dial indicators. Okay, we have now for the vibration test removed all the setup from the static test because we would like to have the frame vibrating free so that nothing is obstructing, and of course the dial indicators, since mechanical, would add additional damping to the system, and what we would like to have is the inherent damping of the structure itself. So now the frame can vibrate freely, and to measure the vibration, to get data on it, we are using an app on a smartphone. We are placing that phone on top of the frame at the top level. We fix it and then we excite the frame, and then we can measure very nicely the vibration. So this is actually from a test of the vibration of the frame in all 3 axes. We are of course mostly interested in the main direction, so in the plane of the frame. So, and this data we do get from here, so will give us the information about the vibration frequency. We will compare that to the theoretical calculation based on modal mass and modal stiffness. And we can also use the decay of the vibration to make an estimate of the damping. Damping is actually something on real structures which is really, really difficult to estimate. There are values in books, but real structures do behave different. And let's see how it works here on the frame. So this is now the top of the frame, and we have calibrated. So, and this is also what we will do here in the exercise. We will calibrate the smartphone, and to have as accurate data as possible. So, and how it runs is in principle we can start the sampling, so then we have a delay of 3 seconds in which we can excite the system. So now I have excited it so that the acceleration is actually out of scale, but we can adjust sample frequency, we can adjust the sampling time. So, and what is already displayed here on the screen is that we have the blue one is the main direction, so this is the axis in which the frame is vibrating, and then of course we have obviously vibration also in the other direction. Also that is not untypical for real structures, even though this is a experimental setup, so that structures do not necessarily vibrate exactly only in one direction, so which means that one vibration form, one fundamental mode can also vibrate in different directions compared to the axis we describe the structure with. So we are through with the introduction to this exercise. So you got now an idea about what you're going to do, in which sequence you are going to do. Details we will describe, of course, at the exercise. So, and an important thing always to remember, so bring your own cameras or phones to document the exercise. So this is very important for the reporting so that you have a description of the test setup, of the different stages of the test setup. So we have here different phases. So that you have material. You do not need to have all photos you make, so, but if you do a lot of documenting, and of course you have to measure it anyway at the start, so then you have enough and appropriate material for later documentation. So thank you very much for your attention, and let's see you again here in the laboratory.